The challenge of being the last speaker is the previous speakers sort of stolen my thunder and covered a lot of what I'm supposed to talk about. So they've covered V-loss, BV-loss, EV-loss, and I'm now at a loss for words. So I think I have put together some slides that might be unique, so let's give it a go. So the topic is long-range aircraft and BV-loss operations. Just before I kick off, a bit about the company Aerovision Africa. We're a solutions-centric company, so we focus on selling solutions to customers' problems using drone technology. And the business model that we have is a solution is made up of 4 key components. The one is the set of sensors, which is the data gathering technology, which is really what makes it all possible. Then, depending on circumstances, weight of payload, etc., we then look at the aircraft. There's usually software involved. We are also the resellers for Pix4D, the photogrammetry processing software. And then lastly, it's wrapped around a set of services. Okay, so I don't know if I can answer that now. I think Dale answered that really well, so I'm not even going to attempt to go through that. Just refer, if you can remember her presentation, just refer to slides 2, 3, 4, 5, and if you can't remember those, I think the presentation will be copied to you. So the current BV-loss capabilities that we have on offering, our entry level is the DJI Matrice 200. So that's got a maximum range. You'll see 2 ranges there, 3.5 kilometers and 7 kilometers. Those of you that are familiar with the DJI technology, if you go and look at your specs, you'll see it says maximum transmitting distance, 7 kilometers FCC or 3.5 kilometers CE. So what is that? FCC is the US standard for maximum transmission, and their standard has been designed to protect their spectrum. The CE standard is the European standard. They have reduced, and theirs focused more on safety. In South Africa, we conform to the CE standard. So when you do open up your DJI Phantom or your Matrice 200 and you read the first spec of 7 kilometers and you fly and you hit the limit of 3.5, it's not a warranty issue, it's not a fault, it is actually a restriction in our particular geographic area. The aircraft we have on display in the exhibition area, in fact, it's the first time that aircraft has been exhibited in South Africa. That's the Alti Transition. That has a standard range of 40 kilometers radio line of sight. And then we have a helicopter that has got a capability of 50 kilometers radio line of sight. Incidentally, the Alti Transition has got 2 upgrade radio link packages that will push that limit to 75 kilometers and 135 kilometers. The same manufacturer are busy with their next range of aircraft, which is the Alti Reach. So just to give you an idea, the difference in size, the middle one is the Alti Transition, which is the one outside in the exhibition area. And the Reach is going to have a wingspan of about 6 meters. It's going to have a 24-hour plus endurance on a single flight, a 7-kilogram payload, and again, it's going to have those various radio link packages starting at 40 kilometers and going to 135 kilometers. So in practical terms, let's take that aircraft in the exhibition area, the Alti Transition. What that aircraft is capable of, and to put it into some perspective, the middle of the circle there is the Vodacom world. At the edge of the 40-kilometer radius, right at the top there is Hartbeespoort Dam. So those of you that are familiar with the area will know that Hartbeespoort Dam is quite a way away. So this aircraft can take off here. It can fly to Hartbeespoort Dam to its limit. Let's call the limit about 40 kilometers. That flight at its cruising speed of about 72 kilometers an hour will take just under an hour to get there. It will then, say, maintaining a perfect circle around the point of interest, which is where we are, could fly a circumference of around about 250 kilometers, which would take about 3 hours and 45 minutes to do. So the mission, it will be able to fly to Hartbeespoort, it'll be able to do that circle twice and then fly back here, and that's a 9-hour mission. It can do that all in one flight. That is the capability of this aircraft. Its maximum ceiling operating height is 12,000 feet. So those of you in the know will know that that aircraft is capable of operating in the airspace together with other manned aircraft. So what the key challenges with BVLOS is, how do you operate that safely without going into all those safety standards? But in effect, how do you detect the aircraft and how do you avoid? And that actually works both ways. It works both from the pilot sitting in the cockpit of the manned aircraft and the drone operator on the ground. Both of them should be able to see each other and should be able to take the necessary avoidance measures. So you've heard about TCAS. Effectively, what is TCAS? So how is manned aviation handling the detect and avoid? So quite simply, most aircraft are fitted with a transponder. It's mandatory for aircraft of a certain weight category and carrying passengers. ICAO mandates aircraft over 5,700 kilograms and carrying more than 19 passengers to be fitted with a TCAS system. In effect, what it is the two radar systems are talking to each other. The transponders detect the respective aircraft, and the pilot is warned of an aircraft approaching its safety zone or safety space. Where the pilot doesn't take the necessary avoidance measures, then the TCAS will actually instruct the flight controller or the autopilot to take avoidance measures automatically. So the flight controller will steer away, and both aircraft will steer away from each other according to the pre-programmed parameters. So what is a transponder? Those that don't know, especially it's a new topic in the drone industry. A transponder is an electronic device that sits in an aircraft. Air traffic control or radar on an aircraft will send out an interrogation signal, and that device will pick up the signal and it will respond, or it will do a ping back and it will send certain information back to the interrogator. There's three types of transponders. Mode A, and what Mode A does is it simply returns what is called a squawk code. And the squawk code is provided by air traffic control to the pilot. Mode C is a little bit more, it provides a little bit more information. Not only does it send back the squawk code, but it will also send back the pressure altitude of the aircraft. So now air traffic control will know at what height that aircraft is. Mode S, or Mode Sierra, sends a little bit more information. It'll now send the registration number of the aircraft, the unique ICAO number, so every aircraft has a unique ICAO number, the squawk code, and then the actual altitude. It's interesting to note that in South Africa, that Mode C is the standard, or seems to be the standard from the little experience that I've had working with ATC. So enter ADSB. So what is ADSB? ADSB is a new standard of transponders. It's been mandated by the FAA. It's becoming a standard in 2020 that all aircraft entering US airspace in those particular airspace classes and at certain altitudes above 10,000 feet above sea level must be fitted with an ADSB transponder. In Australia right now, it's currently mandatory in certain parts of their airspace to have ADSB transponder fitted. It's mandatory for some aircraft in Europe from 2017 already, and Canada is already using ADSB for limited air traffic control. So what is ADSB? At least that is a unique answer this morning, and or a question, and I have the answer, but I'll let someone else sound. Can we get a bit of volume, please?
The world of aviation continues to evolve towards satellite technology to improve safety, communication surveillance, and navigation. By extending the protection of the 1090 MHz frequency to satellites, significant safety gains can be made that will have an immediate impact as early as 2017. Since the 1940s, radar has been the primary method to monitor aircraft movements, and it remains so until today. In recent years, ADS-B has become a widely accepted means of surveillance, providing critical information to stakeholders. Current systems are limited to land-based areas, leaving 70% of the world uncovered, creating inflexible and inefficient routing over much of the world's airspace. These global blind spots will soon disappear. In 2017, ADS-B receivers on satellites will relay signals from all ADS-B-equipped aircraft to air traffic controllers worldwide. This will provide near real-time visibility of ADS-B-equipped aircraft in any flight information region, including in currently unsurveilled oceanic, polar, desert, and mountainous airspace. Space-based ADS-B will enable the optimization of flight paths, increase operational and fuel efficiency for airlines, lower emissions, expand air traffic management efficiency and capacity, and significantly enhance safety, all with little investment in infrastructure. Space-based ADS-B receivers will leverage existing and proven 1090 ADS-B transponders and allow all stakeholders to meet calls for performance-based global flight tracking and safety. With the adoption of space-based ADS-B surveillance, no aircraft will ever be lost again.
Okay, so the fundamental difference between a normal radar-based transponder and ADS-B is ADS-B doesn't rely on an interrogation. So ADS-B calculates its position, its GPS position from satellite, and it broadcasts once a second. So it tells the world, here I am, here I am, here I am. Whoever then has a receiver, be it in an aircraft that has ADS-B in a receiver or ATSC, they will be able to receive that information in real time. Similarly, with a drone flying either in VLOS or BVLOS, exactly the same technology is now available for drones, and it works on exactly the same principle. The GPS, it'll determine its position via satellite and get its GPS coordinates. It will then transmit, and those signals will be picked up by aircraft, by air traffic control. And similarly, by having a GPS ADS-B receiver on the ground, the drone operator can pick up the signal from their own drone and from other aircraft in the area. And how simple is that? So this is an ADS-B receiver. It takes a normal USB power. For manned aviation, you can put this put it on the inside of the cockpit. It's got a little suction cap there, and you connect to it via Wi-Fi with an iPad running an electronic flight bag application. And what that'll provide you is your own position, other aircraft, be that drones or other manned aviation or manned aircraft. So that's as simple as it gets. To give you an idea, most airliners today are fitted with an ADS-B transponder. So last night, that was a screen capture of the air traffic over the Arabian Peninsula. You can go to this website, make a note of it. It's called flightradar24.com. And that'll show you any place on Earth, the real-time air traffic, when I say real-time, within a couple of minutes, of what aircraft is in the air at that time. So that is Europe at 9:20 last night. And if you had to zoom in, say, around any area, I chose London Heathrow, and you click on any of those icons, on the left there you will see the additional information on that particular aircraft. So in this case, this is a British Airways BA913. It's an Airbus 319. That writing is really small. It'll give you the real-time altitude. It'll give you the heading. It'll give you the speed. It'll also give you the time and where the aircraft took off from, and the estimated time of arrival and where the aircraft will land. That's all coming through ADS-B. It's a lot more information than through radar. Being a solution-centric company, we offer a full solutions portfolio of ADS-B technology. So both for unmanned and manned, for unmanned operations, going through to solutions for air traffic control as well. So this is a possible solution for the problem at hand, is how do we coexist with manned and unmanned aviation. And that's to have this technology fitted on every airborne craft that takes off. Something as simple as this. This is the ping station, an all-weather ADS-B receiver. This will pick up ADS-B traffic up to 150 nautical miles. The cost of this, about 30,000 Rand. This could be installed at air traffic control, a simple computer running Windows and running software that would provide that map that I showed you now in real time. It's quite interesting to note that one of the airports closer to us, their air traffic control has no instrument or technology to tell them what is in the air. Everything is based on radio communication and visual sighting. Also, the technology provides today a direct interface or a standard interface to the Pixhawk flight controller, and that provides a TCAS solution for the drone industry. It does the sense, it calculates the distance, or it picks up the signal from approaching aircraft. That could be a manned aircraft or it could be a drone. It does the calculation to see at what point is this now encroaching into my space, and then it does automatically avoid. It'll move out of the way. So in practical terms, we've actually done some tests here in South Africa. On the left, and you can go and have a look at the technology. I've got it on display in the exhibition area. We put a full Mode C, Mode S transponder with a GPS and barometer on an Inspire. And our first customer put it onto a DJI Phantom 4. It's one of the ROC applicants. They're going to be doing work in controlled airspace, and Part 101 currently makes it mandatory for a drone to have a Mode S, just a Mode S or Mode C transponder. So quite literally, this technology can now be put onto something like a Phantom 4, and this is not talk. There's the picture to prove it. One of the tests that we did do was, those of you that know the area, Pretoria Radio Flyer, we touched on that yesterday. I'm a member of the Pretoria Radio Flyer Club. We used the Inspire drone, fitted with the Mode C, Mode S transponder. We contacted OR Tambo Tower and Waterkloof Air Force Base. We got a VFR or a squawk code from OR Tambo. We programmed that code into the transponder, and we just took it up to a height of 120 meters above ground level. CAA, yeah, that's within the regulations, by the way. And we just did a little bit of a circle, but as we hit that altitude, we got confirmation from both towers that they picked us up immediately. They were able to pinpoint our position, and they were able to confirm the pressure altitude, which is more important than the AGL. As you know, manned aviation flies on pressure altitude. So at that area, we were at about 5,500 feet.